Scientists have discovered a massive void in the universe, and Earth is located in the middle of it. In 1981, it was found that about 80% of the observable universe consists of these voids, vast stretches of emptiness. We are situated right in the center of one of these enormous gaps. This emptiness is expanding at an accelerating rate, raising concerns that it might eventually tear the universe apart. What exactly is this void? Where did it come from, and why is it growing so rapidly? Stay tuned as we explore how scientists identified the largest void in the universe and why our planet is right at its core. In the late 1970s and early 1980s, astronomers conducted redshift surveys of galaxies. A redshift survey measures how much the light from a galaxy shifts toward the red end of the spectrum, indicating how fast the galaxy is moving away from Earth due to the universe's expansion. This shift allows scientists to gauge distances. The further a galaxy is, the faster it moves, making redshift a tool for measuring cosmic distances. By mapping the positions and distances of numerous galaxies, astronomers aim to create a three-dimensional map of the universe and understand the large-scale distribution of galaxies. In 1981, Robert Kirshner and his colleagues at the University of Michigan, including Paul Schetter, Augustus Umler, and Stephen Shetman, were engaged in this work when they discovered what is now known as the Boots Void. Robert Kirshner and his team were conducting a redshift survey of a specific region in the Boots constellation. They used telescopes to gather spectral data from galaxies, which allowed them to measure their redshifts and determine their distances from Earth. While plotting the position of these galaxies, they discovered a remarkably large and nearly empty region, which later became known as the Boots Void. This void, spanning approximately 250 to 330 million light-years in diameter, had significantly fewer galaxies compared to surrounding areas. Initially, the team was confused by these results. They later re-examined the galaxy distribution within the void and its vicinity to rule out observational bias or incomplete data. Their analysis confirmed that the void was a genuine and significant feature of the universe, not a result of their survey methods. Kirshner and his colleagues published their findings in a paper titled A Survey of the Boots Void in the Astrophysical Journal, which outlined their survey methods, the discovery of the void, and its implications for understanding the universe's large-scale structure. Following the discovery, additional surveys and research were conducted to map other cosmic voids and understand their characteristics. Advances in telescope technology and data collection, such as the Sloan Digital Sky Survey, have enabled astronomers to create more detailed maps of the universe and study voids like the Boots Void more thoroughly. When you zoom out from familiar scales like your room, house, or city to much larger ones like solar systems, star clusters, and galaxies, an intriguing pattern emerges: a web. This cosmic web might sound like something from a Marvel movie, but as you zoom out further, galaxies, each with hundreds of billions of stars, appear as mere dots of light. The cosmic web consists of long, thin filaments of galaxies stretching across millions of light years, and dense, massive knots of thousands of galaxies known as galaxy clusters. The cosmic web represents the largest structure in nature, filling the universe completely. It's a vast, nearly overwhelming structure that also seems as delicate as strands of silk. Among the web's latticework, there are immense cosmic voids like the Boots Void. These voids, ranging from tens to hundreds of millions of light years across, are the true deserts of the universe, almost devoid of matter. This means that, by volume, most of the universe is essentially empty. As will be explored later in this video, this emptiness can hold significant power. The Boots Void is located about 700 million light-years from Earth. Its diameter of approximately 330 million light-years is so vast that our galaxy could fit into it billions of times. Initially called the Great Nothing, it's now known as the Boots Void, named after its location in the constellation Boots, which represents a herdsman driving a plow around the North Pole. Since this discovery, surveys have produced more detailed maps of our universe. We now understand that galaxies form a vast web with long lines of galaxies acting as threads. In between these threads are massive empty voids with few galaxies. These voids make up about 80% of the observable universe, with most measuring between 30 and 300 million light-years across. Among them, the Boots void stands out as one of the largest, earning it the title of supervoid. It's believed that Boots resulted from the merging of smaller voids. To grasp this, consider the beginning of everything. About 13.8 billion years ago, there was no cosmic web, no galaxies, and no stars. Initially, the universe was composed of fundamental components: dark matter, hydrogen, helium, and a small amount of lithium. It's believed that these components were once densely packed together, forming a uniform distribution throughout the universe. Over time, random quantum fluctuations began to create variations in the matter's distribution. Some regions became slightly denser, leading to stronger gravitational pulls that attracted more matter from less dense areas. This process continued, with denser regions growing even more concentrated. Over hundreds of millions of years, these regions developed into the first stars, galaxies, and clusters. As matter accumulated in these dense areas, the surrounding regions eventually became voids. As the cosmic web grew and evolved, however, while these regions are referred to as voids, they aren't exactly empty. There are still some dim, scattered dwarf galaxies floating around in these mostly empty areas, and dark matter and some hydrogen have also managed to cling to life inside these cosmic and celestial deserts. But, by and large, the voids really are mostly void. And because of this voidness, ironically, the voids are filled with one thing: dark energy. The term dark energy is used to describe the phenomenon of the universe's accelerated expansion, as well as the unknown force responsible for it. While the nature of dark energy remains uncertain, the most plausible hypothesis, suggested by scientists, states that it's closely linked to the vacuum of space-time. Dark energy appears to be present wherever there's a vacuum. Technically, the room you're currently in contains dark energy, as it's present in the small voids between and within atoms. However, dark energy possesses a relatively weak force, which makes it susceptible to being masked by the mere existence of almost anything else, such as matter, radiation, or even mundane objects like dirty socks in the corner. You don't directly experience or perceive dark energy because of the prevalence of matter in your surroundings. However, the voids in the universe are where dark energy has its most significant effects. These voids contribute to the accelerated expansion of the universe. They exert physical pressure on their surroundings, causing galaxies to move apart and disrupting the cosmic web that took billions of years to form. To understand these voids, we need to grasp the concept of dark energy, which essentially means examining the void itself. So, what is dark energy? Dark energy is a theoretical form of energy proposed by physicists to explain the accelerating expansion of the universe. It is the dominant form of energy in the cosmos, driving this expansion, yet it remains elusive and mysterious to scientists. Dark energy can be thought of as the counterpart to gravity, providing a negative pressure that fills the universe and alters the fabric of space-time. Unlike the gravitational pull of dark matter, dark energy accelerates the separation of cosmic objects. It's estimated to make up about 68 to 72% of the universe's total energy and matter, overshadowing both dark matter and ordinary matter. At present, the question of what is dark energy remains largely unanswered, which might seem unsatisfactory. However, scientists have proposed several theories to explain it. One idea is that dark energy could be related to the vacuum energy of space, where particles spontaneously appear and disappear. Another theory suggests the presence of a fifth force that might be responsible for the negative pressure causing the universe's accelerated expansion. Several theories propose different types of fields to explain dark energy, including tachyon fields, which involve hypothetical particles traveling faster than light and potentially backward in time, and a low-energy field known as quintessence, among other concepts. However, these ideas remain speculative, and our understanding of dark energy largely comes from observing its effects on the universe. Scientists consider dark energy essential to the universe because about 25 years ago, it was discovered that the universe is not only expanding, but that this expansion is accelerating over time. This acceleration has been occurring for the past 5 billion years, causing galaxies to move away from each other. While observations support this accelerating expansion, scientists still seek an explanation for this trend. What is known is that the factor causing this effect must be a substance or field that counteracts the pull of gravity and is distributed throughout space-time. In 1999, physicist Michael Turner coined the term dark energy to describe a hypothetical component of the universe's energy budget. This term was crucial because it explained the observed acceleration in the universe's expansion. Without dark energy, the expansion rate would slow down, eventually leading to a collapse and a decrease in the distance between galaxies. It's important to understand that our cosmological model predicts an expanding universe, which supports the concept of the hot Big Bang. However, the expansion rate is not constant, it's actually increasing. This accelerated expansion suggests that an additional factor, which was not significant in the early universe or during galaxy formation, is driving this change. Since scientists cannot directly measure or identify this factor, creating experiments to detect and understand it remains challenging. According to most observations, the cosmological constant is the leading candidate for dark energy, often associated with quantum vacuum fluctuations. It's the simplest and most widely accepted explanation for dark energy and is included in the standard cosmological model. However, other possibilities include scalar fields, Galileans, axions, tachyonic fields, and dynamic dark energy models. But what exactly does dark energy do? If it causes the universe to expand at an accelerating rate, shouldn't we notice our coffee mug drifting away or our daily commute lengthening? We don't typically observe such effects because objects bound by gravity, like stars, planetary systems, and even everyday items such as coffee mugs and tables, seem unaffected by dark energy. Gravity remains the dominant force on smaller scales, while dark energy primarily influences the vast expanse of the universe, driving its overall expansion. This phenomenon is observed by studying galaxies and other celestial objects separated by vast distances, ranging from millions to tens of billions of light years. The greater the distance between these objects, the faster they move away from each other. To illustrate, imagine marking 3 points on a deflated balloon, with 2 points close together and a third further away. In this analogy, dark energy acts like the air inflating the balloon, overcoming gravity's pull. As the balloon expands, all 3 points move apart, but the furthest point moves more quickly. Similarly, in the universe, galaxies that are further apart move away from each other faster due to the stretching of space between them, similar to the expanding balloon. Despite this separation, galaxies retain their shape and do not spread apart internally, thanks to another mysterious component of the universe known as dark matter. Despite their similar names, dark energy and dark matter are quite different. Both are considered mysterious and difficult to explain, but dark energy is not the energy equivalent of dark matter. Their only similarity is that they're both undetectable directly. Their presence is inferred from their effects on visible matter. Dark matter is a theoretical form of matter that does not emit, absorb, or reflect radiation, making it invisible. The term dark in dark matter is used more literally than in dark energy, reflecting its lack of interaction with light. We know dark matter exists mainly due to its gravitational effects, which help hold galaxies together. Without dark matter's gravitational influence, galaxies would spin apart because the visible matter alone, such as stars, planets, gas, and dust, would not provide enough gravitational pull to keep them intact. What does this mean? While dark energy pushes things apart on a large scale, dark matter helps hold galaxies together on a smaller scale. Essentially, dark energy and dark matter have almost opposite effects on the universe. The universe seems to be in a cosmic tug-of-war between dark energy and gravity, with dark matter being a force on the side of gravity. But what is the true contribution of dark matter to the universe's total energy and matter content? Dark energy is estimated to account for about 68 to 72% of the universe. This leaves roughly 28 to 32% for other components, mainly dark matter and baryonic matter. According to CERN, dark matter outweighs baryonic matter by a ratio of about 6 to 1, meaning about 25% of the universe's energy and matter budget is dark matter. Thus, the matter that makes up stars, planets, and everything visible constitutes only about 5% of the universe's total contents. This highlights why understanding the dark universe is crucial, as it represents about 95% of the universe's composition. So, what evidence supports the existence of dark energy? The first indication came in the late 1990s when two independent teams of scientists discovered that the universe's expansion is accelerating. They achieved this by surveying Type 1a supernovae, which are cosmic explosions that occur when massive stars end their life cycles. These explosions produce light emissions with a consistent pattern, making them reliable for measuring cosmic distances. As the universe expands, light from distant sources stretches out, causing its wavelength to increase. This effect, known as redshift, causes light from very distant sources, which originated when the universe was younger, to shift into the infrared region of the spectrum. Astronomers were studying supernovae to measure the rate of the universal expansion, known as the Hubble constant. They discovered that more distant supernovae, which had exploded when the universe was younger, appeared fainter than expected. This suggested that these supernovae were further away than predicted, indicating that the universe's expansion was accelerating. This finding was later confirmed through additional observations and measurements of the cosmic microwave background, a remnant radiation from shortly after the Big Bang. The redshift of light from distant sources, which revealed the universe's expansion, led to a significant change in Albert Einstein's equations. In the 1930s, Edwin Hubble's discovery forced Einstein to remove the cosmological constant, represented by the Greek letter lambda, from his equations. When Einstein developed general relativity in 1915, he had been surprised to find that it suggested the universe should either be expanding or contracting. Einstein initially supported the idea of a steady-state universe, a view held by many at the time. To address this, he introduced lambda, a so-called fudge factor that he later referred to as his greatest blunder. Lambda was intended as a form of anti-gravity to counteract gravity and maintain a stable universe, preventing it from expanding or contracting. Although lambda was discarded when it seemed unnecessary, it was revived with the discovery that the universe's expansion is accelerating. This finding was even more surprising than Hubble's observations and led cosmologists to reinstate lambda. Today, lambda represents the effect of dark energy, a type of anti-gravity that drives the universe apart rather than keeping it stable. Unfortunately, lambda remains a challenging issue for cosmologists, much like it was for Einstein. The leading hypothesis for lambda involves the vacuum energy of space exerting negative pressure on cosmic objects. This suggests that dark energy is uniform throughout the universe. However, there's a significant issue with this explanation. The vacuum energy predicted by quantum theory is vastly larger, by about 120 orders of magnitude, than the lambda value observed through the redshift of supernovae. This discrepancy has led some scientists to label the quantum field theory estimate as the worst theoretical prediction in physics. Despite advances in both physics and astronomy, this gap persists and even widens, raising further concerns among scientists about dark energy. But this isn't the only reason dark energy is so concerning for many scientists. The mysterious nature of dark energy raises fundamental questions about our understanding of the universe. While dark energy makes up a significant portion of the cosmos, its true nature remains elusive, leading to several pressing issues in modern physics. One major issue is the challenge it presents to our current theories. The disparity between quantum theory predictions and observational data suggests that there's a significant gap in our understanding. Resolving this discrepancy is critical for developing a unified theory that can accurately describe the workings of the universe on both large and small scales. Moreover, the existence of dark energy implies that our understanding of gravity itself might be incomplete. Some physicists propose that modifying our current theories of gravity could help explain the effects attributed to dark energy. However, such modifications would require robust experimental evidence and a comprehensive theoretical framework. The search for dark energy also drives advancements in observational astronomy. Projects like the Dark Energy Survey and the James Webb Space Telescope are designed to gather more data on the universe's expansion and the distribution of galaxies. These observations aim to refine our measurements of dark energy's influence and help identify its properties more precisely. Additionally, understanding dark energy could provide insights into the ultimate fate of the universe. If the current rate of expansion continues to accelerate, the universe could eventually reach a state known as the Big Rip, where galaxies, stars, and even atomic particles are torn apart. Conversely, if dark energy's influence changes over time, it could lead to different outcomes, such as a slowing expansion or a future contraction. So, this seems enough for today's video. Please share your thoughts in the comments below and stay tuned for more videos.